Okay. And so we're going to finish up our discussion of chapter 23, which is also the second part of lesson 15. And as we do, I'm going to go back and we're actually going to cover the last slide that we went over together 2 weeks ago. We're going to go over again with a little bit of some more explanation. There's no more information on the slide, but a little bit more explanation. So here is that slide. What is a buffer system? What is a buffer system? What is a buffer system? So as a reminder, a buffer system is a weak acid with its conjugate base. A buffer system is a weak acid with its conjugate base. Buffer is a weak acid with its conjugate base. Now I need somebody to remind me what a weak acid is. What's a weak acid? Yeah, Joe.
An acid does not release all of its...
Yeah, an acid that does not release all of its hydrogen ions. And so you're like, okay, so if it releases all of it, every molecule of that acid releases or dissociates from its hydrogen ion, it's a strong acid. Anything that's less than 100% is a weak acid. And so right from our definition, we know that there are different levels of weak, right? There are acids that are very weak, like water. Water is a very weak acid. In fact, it'll only behave like an acid in the presence of a base. Okay? Water is a very weak acid. But then you have weak acids that are actually pretty strong weak acids, if that makes sense. Something like citric acid in lemons. Okay? That's a pretty strong weak acid. It dissociates almost 100% of the molecules dissociate from their hydrogen ions. And then water, virtually none of them unless they're in the presence of a base. So there's different degrees of weak. But that should make sense to you, right? So strong, there's only one example of strong. Actually, there are 6 strong acids, but there's only one definition of strong. 100% of the molecules have to dissociate from their hydrogen ion. But now weak, there's different grades. What is the conjugate base? What is the conjugate base? Somebody remind me what that term is.
Something's left over after it's released.
Yeah, after the hydrogen, or after the acid has dissociated from its hydrogen ion, the conjugate base is left over. Okay? And so we have something I'm going to show you, and it's a way that we can represent any acid. Okay? And so what does every acid have? At least all of the acids we've used as an example. All of them. They all had this. Now they varied in the rest of the materials, but they all had this. Hydrogen, right? Because they have to dissociate from their hydrogen. Now we have other ways to represent, I mean, there are things that things can behave like an acid without having a hydrogen ion. They have to encourage water to release its hydrogen ions. But anyways, that's more detailed than what you need. That's if you decide to go into a physical science at the undergraduate level, these are some of the things that you'll learn. So we'll represent every acid as just HA. This is just a general acid. And so the H tells us it contains hydrogen. The A tells us it's an acid. Okay, and this can represent any acid. This is not representing a specific acid because A is not a symbol for any specific element. This is just representing a general acid. Okay? This could be HCl, could be HSO4, could be H2CO3. Okay? Right? Some of those acids that we saw 2 weeks ago. So any acid. Welcome, Charles.
Hi.
Any acid. And then what we're going to represent is what's called an equilibrium. An equilibrium. Because we are representing a weak acid here, and this is not going to be representing a strong acid, not all of this acid is going to do this. And that's why we show an arrow that's actually pointing in both directions. Because if it were a strong acid, we would just show an arrow going to the right, and everything to the right would be what you get. But this isn't a strong acid. I'm using this to represent a weak acid, or just any acid in general. Not all acids are strong. So we need our arrow to point in both directions. Okay? Does that make sense? And then what it's going to do, since it's an acid, it's going to dissociate from its hydrogen ions. Okay, so HA is going to become H+, and what's left over, which would be A minus, and this is the conjugate base. And why is this A minus and not just A?
Because the H took a positive charge.
Yeah, the H is positive. It started neutral. It lost something positive. It better be negative. Otherwise, if this were just neutral and you put it together with something that's positive, this was going to be positive, right? But if this is negative and this is positive, then it makes sense that they would combine into something that is neutral. Okay? And so now we've represented really any acid there with our HA, and what's going to happen? It's going to dissociate. It's going to dissociate from its hydrogen ion, leaving us the conjugate base. Hydrogen ion is positively charged, conjugate base is negatively charged. Now, again, the arrow points in both directions because if we're representing any acid, some acids are not going to completely dissociate. But they will reach some kind of equilibrium. Though you put this acid into water and it'll start to release hydrogen ions until it gets to a point where it's not going to release anymore, based on whatever the strength is of that acid. And at that point it will reach what we call equilibrium. Okay, it will reach what we call equilibrium. Now notice, we said a buffer system is a weak acid plus its conjugate base. So this whole thing together is a buffer system. It looks just like this. Some of the weak acid has been converted into conjugate base, some of it's still sitting as weak acid. If it were a strong acid, there'd be none of this left, right? It would have entirely converted into hydrogen plus the conjugate base. Because that's what strong acids do. 100% of the molecules give their hydrogen ions. Yes? That's a strong acid. But this is a weak acid with its base. So we get some equilibrium. And so if it's a really strong, weak acid, and I know that might be confusing, but I think that makes sense, right? A strong, weak acid, like citric acid, there's going to be very little of this and a lot of these. But if it's a very weak acid, like water, and with a base, there's going to be a lot of this and very little of this. Okay? Sound good? Make sense? Okay. But every acid's going to have its own equilibrium point. And guess what we call that equilibrium point? We call it the Ka, which is the dissociation constant, which is basically how much of it dissociates from its hydrogen ion. Okay, and every acid has a very specific Ka. Right? Is it all coming back? I know it's been a couple of weeks, and there's been several days of rain in between when we met last. Actually, there's probably only been one day of rain in between when we met last and today. We didn't have rain for a while. And it's been nice and warm. I think it was 82 degrees on Monday. It was amazing. It was so hot, people were complaining about it being hot. And I'm like, this is Southern California. Like, this is what we signed up for, 80-degree days. Sorry. This is another thing we talked about 2 weeks ago. When the pH of a system moves towards the acidic end, that is, we start to lower the pH, the conjugate base is going to collect excess hydrogen ions. Okay? And I'm going to show you how this works in a minute. And we'll round out our discussion of buffer systems. Okay? When the pH of the system moves towards the acidic end, the conjugate base is going to collect some of that excess hydrogen. When the pH moves towards the basic end, the weak acid is going to donate more of its hydrogen ions. So if the pH moves towards the basic end, that is, the pH starts to increase, more of the acid is going to donate its hydrogen ions. And so now you're like, it sounds like our equilibrium was disturbed, right? Because if we've got this weak acid and its conjugate base, it's going to establish some equilibrium, right? That's specific for that acid. But now we're starting to disturb it, right? Shifting it towards the acidic end, shifting it towards the basic end. We're doing something to it. Do you understand that language there on these slides? It's something we didn't mention a lot. And again, we'll see this again, and I'll show you what's actually happening. Because you're like, Dr. Eagle, right now it just all seems like It's up in the air. It's theoretical. Let's see it happen. I want you to show me how would we shift it towards the acidic end? How would we shift it towards the basic end? And ultimately, this buffer exists to balance and maintain pH. So when we have a weak acid along with its conjugate base, we have a way to buffer against changes in pH. Right? We start to shift it towards the acidic end, the conjugate base will take some extra hydrogen ions. We start to shift it towards the basic end, that weak acid is going to release more hydrogen ions. Okay? And the system ultimately works to balance and to maintain pH. And I want you to think about this. Why would you ever need to balance and maintain pH? Why would you need to do that?
Because it could have catastrophic consequences.
Absolutely.
Like the atomic bomb.
The atomic bomb. Maybe not that catastrophic, but definitely.
Close.
Maybe so. So have any of you had ceviche? I asked this on Monday and nobody had eaten it. And maybe you have, but you don't know what it's called. So ceviche it's a dish. It's like pico de gallo, where you've got chopped up tomatoes, chopped up onions, some cilantro, maybe some avocado in there, and then a lot of lemon juice or lime juice. And then you put raw fish in it, and the acid from the lemon cooks the fish. You're cooking fish without heat, because the acid does something similar heat does to the proteins. And you're like, wait a minute here. Does that mean if something in my body got really acidic, it would start to cook my tissues? And the answer is yes. And it's not good. And that's what happens when you get cramps. Well, one of the things that happens when you get cramps or you get soreness, you're building up acid in your muscles and it's starting to cook your muscles. And it doesn't feel good. And you've got to now repair those muscles. And so that's when you work out, you stop getting sore, is because you increase blood flow to there and you do a much better job of getting rid of that acid that builds up and washing it out, diluting it. Okay? And you're like, that sounds awful. And this is why we have buffer systems in our body, so that the pH doesn't get too low and you don't start to cook your tissues. Or the pH doesn't get too high, which will also cook your tissues. Either way, it's just not good.
So basically, when you're working out, you're literally cooking your muscle.
Yeah, unless you're in really good shape and you do a really good job of keeping your muscles, giving your muscles plenty of oxygen, and getting really good blood flow to wash away any acid that's building up. But yes, if you get sore after doing something, and it's not like, some sores like joint soreness, and that's because of inflammation. Like, if you're throwing a baseball and then your shoulder is sore the next day, that's a different thing. That's inflammation, which can also be devastating. But like if you're throwing a baseball and the next day this muscle is sore, your biceps, it's sore because you partially cooked it. Because you built up acid in it and it partially cooked it, and now it's got to heal. It's basically you lose that portion of your muscle. It's got to be rebuilt. It's got to be rebuilt.
Which can take a long time, I guess.
It can take a long time, and that's why soreness can linger. Depends on how sore you are, how hard you pushed your body. Yeah.
Isn't that normally painful because it builds back more? than
Yes.
it originally had?
Yep. Yeah. So our bodies are designed such to meet greater than the challenges you expose them to. And so our bones do this as well. So your bones are constantly remodeling. Your bones are constantly breaking down matrix and rebuilding it. And the more pressure you put on your bone, the thicker they get. So when you look at like the bones in the hand and the arm of a boxer, they're way thicker than a person equally sized, because they're putting additional strain on it, and our bodies are designed in such a way that they will meet a challenge greater than the one you're exposing it to. And so, yeah, absolutely. Your muscles will end up bulking up. They'll get bigger. Your blood flow will increase to those areas, so you do a better job of keeping those muscles oxygenated so that they don't make acid, and flowing any acid that does get made away. Yeah, Tom?
Also, that works the opposite way, or if you stay in space for too long, your bones will go.
Yep, your bone density will decrease. Yep, so yeah, this is something that keeps the astronauts and the cosmonauts from staying too long at the space station. And so cosmonauts, those are Russian version of an astronaut, by the way. I think does the Chinese, do they call their personnel cosmonauts as well? Anyways, the Russians do. And the Russians and the Americans and the Chinese are the most common people up at the space station. But yeah, that's one of the things that keeps them from being up there too long. Because if you're not exposed to the amount of gravity we experience on Earth, you're putting less pressure on your bones and your bone density will decrease. Yeah. All right. So what is a buffer system? Just write C first point. This is the way we answered it 2 weeks ago. This is the way we will continue to answer it. C first point. C first point. And that's what a buffer system is. And so the next question is, how does a buffer system maintain pH? How does a buffer system maintain pH? I'm sorry, real quickly, I need to step out and take this call. I'll be right back.
If you muscle then where did you muscle work out right before the meat comes out. Yeah. Yeah. And it's just hard sour.
Yeah, I wonder if it's possible because we work on so hard. Your muscles produce enough.
It's also
Consume so much.
Yeah. Because the one class right like for us, no, it would take so much time.
when you're at the stage, it's actually
Monday.
too long.
Oh, it's Tuesday. Yeah. I didn't try fast. No, yeah, stop at least. I don't know.
So like your tracks when you
I didn't take
start
one
moving,
time.
so then you cover the arms, so you can put your arms, you can't move by. So when you're doing
I wonder if that's what they do to dissociation more I guess Ross should say that back for you.
How long?
Yeah, like my intestines are feeling now. Not feels right over your intestines.
Sorry about that. What's that? Electrical issues. Sorry. It's not your fault. It's mine, but so how does a buffer system maintain pH? All right, so the weak acid neutralizes hydroxide ions. The weak acid neutralizes hydroxide ions. And so let me show you this. Flo, go ahead and write that down and then I'll show you something. The weak acid neutralizes hydroxide ions. So let's say this is our buffer system, right? It's a weak acid along with its conjugate base. This is our buffer system. We put a strong base in here, something like NaOH. And look at it, NaOH is only going to have an arrow going to the right because it's a strong base. So 100% of this base, 100% of the molecules dissociate. And you'd be left with sodium ions and hydroxide ions. Okay, 100% of it. That's what a strong base does, right? Just like a strong acid dissociates from, or 100% of our strong acid molecules dissociate from hydrogen ions, 100% of our strong base molecules dissociate from their hydroxide ions. Okay, so if we add this, we add a strong base to our buffer system, what are we going to get a lot of?
Water.
Well, we're going to get a lot, initially we're going to get a lot of this. Eventually we'll get a lot of water. But you're working ahead. Okay, so eventually if we put this strong base into our buffer system, initially we're going to get a lot of hydroxide. Okay, and hydroxide ions raise the pH, right? Our POH is a measurement of it's a negative logarithm of our hydroxide ion concentration, and the higher the pH is, or the lower the POH, the more basic it is, right? The lower the POH, the higher the pH, the more basic it is. So if we put this into our buffer system, initially we're going to get a lot of this. Does that make sense? Okay? Well, what's going to happen is these hydrogen ions in our buffer system are going to react with this. They're going to eat it up. Our hydrogen ions are going to eat up all of these hydroxide ions we've now added to our solution, because that's what hydrogen ions do. They combine with hydroxide to form water, right? We've seen this before. So these hydrogen ions are going to eat up all of this hydroxide that's showing up. But now what's happened is we've made less of this, right? Does it make sense? We now have less hydrogen ions because those hydrogen ions are eating up this hydroxide we're adding to the solution. And so now it's going to be, it was at equilibrium before, but now we have less of this. So it's going to shift the reaction in that direction to replace the hydrogen ions we've lost. Because at equilibrium, there's a certain amount of this and a certain amount of this. There's a certain amount of this and there's a certain amount of this. If we have less of this, we need to make more of it. Yeah, Josh.
The A minus, once you get excess of A.
You will get excess of A minus. Yep. And that's just, it's a byproduct of these buffer systems. So yes, if you add hydroxide to this solution, and you start to gobble up hydrogen ions, and you start to convert more of your weak acid into this, you are going to get excess conjugate base. But the conjugate base of a weak acid tends to also be a weak base. So it tends to not be something catastrophic to have around. But yes, you will get an excess of conjugate base, absolutely. Does that make sense? Because this is eating up this hydroxide we're adding to the solution, and so we need to replace that. More of our weak acid will dissociate, and that's what we say, the weak acid neutralizes our hydroxide ions. Okay? And so the weak acid is going to neutralize those hydroxide ions. Well, the opposite is true when we start adding an acid. So let's draw this is our same buffer system. And why is the arrow pointed in both directions again? Because it's a weak acid. It's not completely dissociating like this strong base does. Okay? Right? That makes sense? So this is weak. Some of it dissociates, not all of it, and it reaches some equilibrium, where some of it's still as the acid and some of it's as the conjugate base. Okay, well now let's put a strong acid in here. Let's say we put something like HCl into there. Let's say we put something like HCl into there. We put something like HCl. HCl is a strong acid, so it's going to fully dissociate. The arrow's not pointed in both directions, it's only pointed to the right. It's a strong acid, HCl. So it fully dissociates. If we add this to our buffer system, we're going to get excess hydrogen ions. Okay? We're going to get excess hydrogen ions. Okay? Well, our conjugate base is going to eat this up. Our conjugate base is going to eat up those extra hydrogen ions. Now, here's where it gets a little weird, because we can't just shift the formula in that direction to recruit this. Because if we do that, we're just going to keep making more hydrogen ions, right? Which is going to keep exacerbating the problem. So when you do this, start adding a lot of hydrogen ions, some of these are eating it up, but some of these are increasing. It's not eating all of them up. Okay? So the conjugate base, just a moment, Joe. The conjugate base, it's eating up these extra hydrogen ions, but not all of them. And some of them are increasing this, and so it actually shifts the reaction in this direction. Because now we're starting to get more hydrogen ions, and so we shift it back in that direction, and now, like what you asked Josh, in this situation, are we going to get an excess of conjugate base? And the answer is yes. In this situation, we're going to get less conjugate base. But again, it's a weak acid and it's a weak base. We can handle that. What we can't handle is this changing very much. Because this changing changes the pH, right? If this goes up, pH goes down, it becomes more acidic. If this goes down, pH goes up and it becomes more basic. So we can't really handle this changing. We can handle these changing. That's okay. But this changing is not good. So if we have excess strong acid, we're going to get a lot more hydrogen ions, and it's going to have to shift the reaction in this direction. So now we're going to have conjugate base eating up some of these hydrogen ions and eating up, just shifting it back in that other direction. Joe?
So if you get a weak base and like a conjugate acid.
Yes, you could do that. Yeah, that's what a buffer system is. A buffer system is a weak acid and its conjugate base. It's also a weak base and its conjugate acid. Yeah, that's a good question. It's both. Because the conjugate base of a weak acid is still a weak base. We're getting some thunder. This is real. This is real. Okay.
Wait for metal objects.
All right. Does this make sense a little bit? So, and then you have to think if we're eating up some of this excess hydrogen ions, that's just going to make more of this, right? Because a conjugate base plus a hydrogen ion is the acid. And so that's why the reaction is going to shift in this direction, even though we're losing one of the products. But here we were losing a product that forces us, that's going to raise the pH. If we lose this, it's going to raise the pH. We need to maintain the pH. That's why this buffer system exists. The only way to do that is to replace a hydrogen ions lost. This is going to make us more hydrogen ions if we put a strong acid in here. And so we need to gobble up those extra hydrogen ions and keep the same amount, maintain pH. Okay? And so this is how the buffer systems work. You put a strong base in, the hydrogen ions are going to eat up those hydroxide ions, and then we'll make more. The weak acid will contribute more. Over here, our conjugate base is going to eat up some of these extra hydrogen ions, which is going to make us more of our weak acid. Shift the reaction in that direction. Yeah?
So pH is basically the amount of H just floating around by itself.
Yeah, it's the negative logarithm of the hydrogen ion concentration. So yes, it's how much free hydrogen ions do you have. Now, in reality, those hydrogen ions are going to be on water molecules, and they'll, as H3O, a lot of them, they won't be free, but they're yeah,
free.
yeah.
And so you add more H, it takes them out, and then you have less H than necessary.
Then you need to make more. Yep. Because you need to maintain the same amount of H. That's the pH, right? The pH is the negative logarithm of the hydrogen ion concentration. So if you lose H, you need to make more. The only way to make more is to have more of the acid dissociate. If you gain H, you need to get rid of it, and the only way to do that is to make more of our weak acid. And so that's why the arrow could point in either direction, because it will shift around based on the needs, based on the environment. Okay? All the while maintaining pH. All the while maintaining pH. All right? And so we can actually calculate this. We can calculate, now I will tell you this, I will never ask you to calculate the pH of a solution using the Henderson-Hasselbach equation. However, I will expect that you know what the Henderson-Hasselbach equation is, and so that you can explain the relationship between a buffer system and the overall pH. Okay, and so we can do this, and here's the formula. The formula for this is pH, the pH of the solution is equal to the pKa of the buffer system, whatever that weak acid is, right? Every weak acid has a very specific Ka, right? We talked about this 2 weeks ago. Every acid has a very specific Ka. And so the pH of the solution is equal to the pKa for that acid plus the logarithm of conjugate acid, so the logarithm of the concentration of conjugate base, sorry, not conjugate acid, conjugate base, divided by the concentration of our acid. And so this is the Henderson-Hasselbach equation. And again, I will not ask you to calculate this. However, I will ask you to know this and to be able to explain a little bit about what this is saying. Be able to explain a little bit about what this is saying. And so what this is saying is if you want to maintain pH at a certain level, and you have a certain pKa that's dependent upon your acid of whatever your buffer system, and you want to maintain a certain pH, you're going to have to play with how much conjugate acid and how much conjugate base and how much acid you have. But I just showed you this on the board, right? That if you put excess strong base, we're going to get less acid and more conjugate base, right? This is what Joss asked. He said, doesn't that mean we're going to have an excess of conjugate base? Yes, we are. But if we put more strong acid in, we're going to get less conjugate base and more acid, right? And that's what's required in order to maintain a very specific pH with a very specific buffer system. Because pH, this is something you need. And for our tissues, most of our tissues, the pH ranges from about 6.5 to 6.8. For most of our tissues in our body, the pH has to stay in that range. It's not a very wide range. If it gets any less than 6.5, tissues will start to cook. If it gets above 6.8, they won't start to cook because that'd be at neutral, but then above neutral, they'll start to cook. And so this is where we need to maintain the pH. But we're working with an acid that has a very specific Ka. And so this ratio will have to change to maintain this range of pHs. Okay? That's all I need you to be able to do from this, but that's exactly what I drew on the board for you and you all have written down, right? If you start adding base and you add hydroxide, you're going to get less acid and more conjugate base, right? If you start adding strong acid, you're going to get less acid and more conjugate base, or less conjugate base and more acid. Okay? Make a little bit of sense? And this equation will tell you what you need to do. And so it gives you an idea that the closer these two values are together, the less you have to manipulate this, right? If you're trying to maintain a pH that's very close to the pKa, you won't have to manipulate this as much. Okay? Which is why we have very specific buffer systems that are designed in very specific ways. All right. Any questions about this?
No.
Okay, so now you should be fully equipped to finish the worksheet from chapter 23 that I gave you, and you should be fully equipped to do quiz from lesson 22. Yeah, Charles.
What's the answer?
The answer? There is no answer. We didn't work a problem. All I did was gave you the formula. And I won't make you calculate. Like I won't give you a specific acid and its Ka and ask you to calculate this. Even on the worksheet. In the worksheet it'll ask you to set this up, but with a specific acid and a specific conjugate base. Because if this acid were HCl, well, that would be a strong acid. That's not a good example. If this, let's say this acid were H2CO3 that we saw a couple weeks ago, then the conjugate base would be HCO3 minus, right? So you may have to set this up by putting the actual acid in and not just HA, which represents some general acid, but to put the actual acid in and put the actual conjugate base in and not just a general term to represent any conjugate base. But other than that, you won't be asked to calculate this. Like I won't tell you, some of it might ask you, what does this term need to be? Like if you want to maintain a pH of 6.5 and your pKa is 5, what does this value need to be? If you want this to be 6.5, this is 5. 5 plus what value is 6.5? 1.5, right? So you may have to do some math like that. but you're not going to actually have to plug in your concentrations and calculate this because it's too much for this level. You go and you take a college chemistry class, you're going to do that. This is not a college level chemistry class. All right? Does it make sense? No questions about buffer system? Okay, Josh, you were saying you had some questions from chapter 21. Is that right? Was that the chapter?
Lesson 21.
Lesson 21. Ethan?
Sorry, what was the answer to this question now? Or is it just,
Oh, that's what you meant, Charles.
yeah, that's what he meant.
Oh my gosh, Charles, I'm so sorry. How does a buffer system maintain pH? You want the answer to that question.
Yeah.
Oh man, I am so sorry. So how does a buffer system maintain pH? And you would just say you would make more or less weak acid. You make more or less weak acid.
That's better than falling down C list.
Yes. Yeah, absolutely. You make more or less weak acid. I'm so sorry, Charles. I was very confused. Nobody on Monday asked me that. That's refreshing. Well, on Monday, we immediately went over into the lab too, so. All right, Josh, you had some questions? So if you all want to pull out your worksheet from chapter 21, Josh has some questions, and even if you were able to do all the questions, I'm sure talking through this will help as you prepare.
So it was like 14.
Okay, question number 14.
Finding the pH
Uh-huh.
of an acid solution when you have the molarity
Of what?
of that acid solution.
Oh, so you have the molarity of the acid,
Okay.
or you have the molarity of hydrogen ions?
So like 12 to 14, it says how many moles of H plus are in this, and then you get the molarity, and then it says what's the pH. And I was talking about the butters.
How many moles of hydrogen ions are in 100 milliliters of acid solution if it is titrated? Oh, okay. All right, so for this, both of those, that one of those is a strong acid, the other one's a strong base. So that strong base is going to completely dissociate, and if we have 20 milliliters of the base, and it's 1 molar, so we know molarity, so we've got NaOH, and its molarity is equal to, what's the molarity? 1 molar?
One.
Okay, so we have 1 molar, which is equal to 1 mole in every 1 liter, right?
You have 20 milliliters.
Yeah, but we only have 20 milliliters, okay? And so what this, if we don't know, so 1 molar is 1 mole in every 1 liter, which would equal, if this was only 0.02 liters, which is what 20 mils is, okay, 20 milliliters is 0.02 liters, because 200 milliliters would be 0.2 liters, 20 is 0.02, okay? And this, we've got a 1-to-1 ratio here, right? 1 mole for 1 liter, so we'd have to have 0.02 moles in 0.02 liters, okay? Does that make sense? Because this is 1 molar, so it's 1-to-1. If we've got 1 mole in 1 liter, but we don't have a full liter, we have 0.02 liters, means we have to have 0.02 moles in that, in order to still have that ratio of 1 molar.
And when you're titrating stuff, it has the exact same amount of acid as the base. Because
Yes.
they have to combine to neutralize.
Yes, so our hydroxide ion concentration is 0.02 molar, right? Because if we had 0.02 moles of sodium hydroxide and it's a strong base, it's going to completely dissociate every molecule. So we're going to have 0.02 moles of hydroxide ions. Yes? And then if we're going to balance this out with hydrogen ions, it means that our hydrogen ions have to also equal what? 0.02. Because they're neutral. So which means we have as much of this as we have of this. Okay? We have as much of this as we have of this. Otherwise it wouldn't neutralize it. That's what it means when you titrate it out. You're neutralizing it. So if we have this much hydroxide ion, we have this much hydrogen ion. And it wants to know what the pH is, right?
That's the third question. So that first one, it just wants to know how many moles of H plus are in 100 milliliters of acid solution that is titrated to 20 milliliters.
This one.
And we got 0.0.
Well, it's this molar, but that doesn't tell us how many moles. That's the molarity, right? And then, but we have how many? We have 100 milliliters.
Of acid solution.
Yep. So we have 0.02 molar is equal to moles over liters, right? Moles over liters. Yes. And we have 0.1 liters because it's 100 milliliters. Do you agree? And we're trying to figure out how many moles we have. We know this. This is what the concentration has to be because it balanced this concentration. Okay? And so this is how much of it we have. If we multiply 0.1 liters to both sides, this will cancel. And I'll work out the math from this one as well in the slides before I send them out. And then so we'd be, this is moles per liter, so liters will cancel, and we'll be left with just moles. And 0.1 times 0.02 is 0.002 moles of hydrogen ions?
Yes.
Yes. But when we go to find pH, we don't care about moles, we care about molarity. Because the third question, so the first question I asked you for just moles.
Yeah, the moles of H plus.
Yep, so this is moles of H plus.
And then the 13th was what is the molarity of the acid solution?
What is the molarity?
You were 48, 13?
13, because you need to find the molarity to find the pH.
Oh, yeah. This one, I messed up over here. This is terrible. I did something really bad for you guys. I'm so sorry. This is moles, not molarity. Right, the molarity of it was 1 molar,
Yes.
right? It was 1 molar. This is in moles. It's 0.02 moles. Which means that this has to be 0.02 moles of hydrogen ions to balance it. I messed that one up. So that's in moles. We have this many moles of hydroxide ions. We have to have that many moles of hydrogen ions to balance them out and form that many moles of water. So this is the answer to the first question, is moles. So there are 0.02 moles of hydrogen ions. And then molarity is equal to moles divided by liters, right? And so molarity is equal to 0.02 moles of hydrogen ions divided by 0.1 liters, right? It was 100 liters, 100 milliliters. And now we'll get our molarity will equal 0.02 divided by 0.1 is actually 0.2 molar. Okay, so that's the answer to question 2. Question 1, the answer is 0.02 moles to balance out the 0.02 moles of hydroxide. The answer to question number 2 is 0.2 molar because we divided 0.02 moles by 0.1 liters. And that gives us 0.2 molar. And then the third question wants to know pH.
Yes.
So the negative logarithm of 0.2. And that you can just put into a calculator. What is it? Negative logarithm of 0.2?
0.6989.
0.6989? Is that what anyone else got?
Yeah,
0.7? Yeah, that works. We'd rounded to that anyways. So the pH of this solution is 0.7. It's really low. It's really low. Does that make sense, Josh?
Yeah.
Yeah, and I'll work that out on this slide as well. So what I put on the board for you all, I'll put that on the slides before I send them out. So you can see, like, if we add acid and we have a lot more hydrogen ions, we've got to shift and make more weak acid. If we add a base and add a bunch of hydroxide ions, we gotta shift and make less acid. Okay, and then I'll show you I'll show you all this. Okay. Any questions? Yeah, Micah.
I've just got a question from the lesson 20 worksheet.
Okay.
I couldn't remember how to do this one problem. 14. It says if OH minus equals 1.0 times 10 to the negative 4, then the hydrogen equals blank.
Yeah, so that's where you have to use this equation here. That Kw is equal to our hydroxide ion concentration divided by our hydrogen ion concentration, which equals 1.0 times 10 to the minus 14.
Okay.
Right?
Yeah, I think so.
And so if it gives you this, we would basically do our hydrogen ion concentration is equal to, no. This is, sorry, the formula is this. Kw is equal to the hydroxide ion concentration times the hydrogen ion concentration equals 1.0 times 10 to the minus 14. This is the equation. So our hydrogen ion concentration is 1.0 times 10 to the minus 14 divided by our hydroxide ion concentration. And if in that one, what is your hydroxide ion concentration? 1.0 times 10 to the minus 5?
Minus 4.
Minus 4. So our hydrogen ion concentration would equal to 1.0 times 10 to the minus 14 divided by 1.0 times 10 to the minus 4. Okay? Which equals 1.0 divided by 1.0 is just 1.0 times 10 to the, when you divide the same base, you subtract their exponents. Negative 14 minus a negative 4 is negative 14 plus 4, which would be negative 10.
Okay.
So your hydrogen ion concentration is 1.0 times 10 to the minus 10. Okay?
Okay.
Does that make sense?
Yeah.
Okay. I'll work that one out too. So I'll work the question you asked, because there's probably several more in that worksheet that asks a similar question. And I'll work that problem out again, Micah, before I send these slides out. I'll send them out in a couple of days. Probably not today, maybe tomorrow. I'll get them ready. All right? All right, everyone. Well, have a wonderful day. Do your very best to stay dry. And I'll send you